A hole is essentially a missing value in the domain where essentially if we were to look at it on a graph, there is a hole in the graph. And it's different from an asymptote where the graph approaches some value and then the graph either shoots up to positive infinity or negative infinity, or it just approaches it but never quite touches it. This is just the graph is going along and in its regular shape, and then all of a sudden there's just an x missing from it. That's what a hole in the graph is. And to illustrate how they occur, I'm going to use the example from the previous video, which is x squared minus 4 over x minus 2. And x squared minus 4 can be factored out into x minus 2 over x plus 2. Now, holes occur when there is a 0 in the denominator that is canceled out by the numerator. So here we can see that these x minus 2's can cancel out. However, and this leaves us with x plus 2. However, x cannot equal 2. And this is what a hole in the graph is. Essentially, the graph of this function is essentially the same as x plus 2. However, there's just a hole in the graph where there is 2. So let's illustrate this. So I have x minus 2 over x plus 2. X minus 2. And we said that the domain, so let's write the domain of this. The domain is everything except for 2. So negative infinity to 2, and then 2 to infinity. And we can rewrite this as x plus 2 if we want to, but we must say that x cannot equal 2. So let's graph this. This is essentially a line. We can start at, we can either use the x-intercepts. We can say that when x is equal to 0, y is equal to 2. And when y is equal to 0, x is equal to minus 2. So like that. And we can, where's my line tool? Oh, there we go. That's not a line tool. So like that. However, x cannot be equal to 2 because it's going to make this whole thing 0. So what I'm going to do is I'm going to go over to x is equal to 2, and then I'm just going to put a hole in the graph. So essentially that's what it looks like. And generally what we do is we put a circle, an open circle, where there is a hole in the graph to show that there is a hole in the graph. Because sometimes these holes can be so small, if you just don't connect it, it's sometimes hard to see that there is a hole there. So we illustrate a hole with an open circle. Now let's graph x plus 2. If I want to graph, let me do it in a different color. So just to compare these graphs, f of x is equal to x plus 2 with no restriction on the x. There's no x cannot equal 2. Oh, well, I'm not going to have a lot of space. Let's move down then. Whatever. Actually, let's not cover it up. Okay. So now I'm going to graph f of x is equal to x plus 2. And the domain is all real numbers, negative infinity to infinity. And it's going to look exactly the same as the other one. We can use our x-intercepts, or we can just start plugging in points. I like using intercepts. So when I say x is equal to 0, y is equal to 2, and when y is equal to 0, x is equal to minus 2. And that's the graph of that. And it looks almost exactly like this one, except the only difference is that there is a hole at 2, and here there is not. So now it's very clear why earlier when we were learning about domains that it was important to write this x minus 2, or this x is not equal to 2. Otherwise it's not the same function. This is not the same as this because there's a hole in that one. And the hole is caused by these canceling out. This is when there is a hole. When we have a domain problem in the denominator, like an x minus 2, and is canceled out. Let's say we had a different function. Let's say f of x is equal to x minus 2, x plus 2, and then how about x plus 3? And then in the denominator I had x minus 2 and x plus 3. So what would this look like? Well, this would look almost exactly like this, where we'd have, well, let's write out the domain of this first. The domain is negative infinity to minus 3. So if we put in a minus 3 here, it will be 0. Minus 3 to 2, and then 2 to infinity. And here again, we're not going to have any asymptotes, because since these cancel, this also simplifies into, I really should have done it in a different color and some more space, but this also simplifies into x plus 2, where x cannot equal minus 3 or positive 2. So the graph would look exactly like an x plus 2 graph, like this one, except we would have an additional hole to this one where x is equal to minus 3, so that would be right here. Yeah, there we go. I don't know why it didn't work the first time. So the graph of this would look like this. There would just be an additional hole for the minus 3. So that's how holes work. It's very simple. The asymptotes are a little bit different, but when we have a 0 that's being canceled out for the denominator because of the numerator, like here or here, that is when we're going to have a hole in the graph.